So this is number, what would we say? This is on page 8. And this is number 13. So we're going to use this proof in a square. That's the only time that we proved that the diagonals were perpendicular. So we're going to use it as an example. And that's number 2 on your square proofs. So the first thing that we're going to start with is rhombus, RSTU with diag, RT, and SU. I guess we could throw in intersecting at point M if you want. And that was all given. Okay. Now, if we look at our proof from the square, step 2 said NO is congruent to NO. And we used reflexive. So we use this common side. So if you look at this proof, we are trying to show these two triangles that are right next to one another congruent. So let's do the same thing here. We want these two triangles right next to one another to be congruent. So if we used, in that one we used that common side, what's our common side in this one? SM. Okay, so SM is congruent to SM, reason? Reflexive. So that's a side. Then in this guy we used a definition, or we used definition of square, and we said MN is congruent to LN. Can you do that in a rhombus? No. What's the definition of rhombus? All sides are the same. So if that's true, then we can claim what? That they are. RS is congruent to TS. Reason? Definition of rhombus. Now in number 2, or in number 12, you proved that the diagonals bisect each other, right? In number 12, so we're going to use that. If you look at this guy, you have this guy, we said ML and NP bisect each other. ML and NP bisect each other, property of a square. So what do we want to say here? R, or S, U, and RT bisect each other. Reason? Property of a square. Or yeah, not square, rhombus. And that would be from number 12, which you proved in number 12. So then what are we going to say? If they bisect each other, then what do we need congruent? This guy bisects this guy. So RM is congruent to TM. Reason? Definition of bisect. So let's use some color action here. We had RS is congruent to ST. That was our blue. We have RM is congruent to MT. That's that guy. We have SM is congruent to SM. That guy. So what do we know about those triangles? Okay, so triangle RSM is congruent to triangle, who goes with R? T. SM. Reason? Side, side, side. Now let's go back to this guy. This guy got side, 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 and then it went to MON. MON is congruent to LON. So what do we want to use? Angle TMS is congruent to who? Angle RMS. Reason? Well, triangles are the same. What do you know about the angles? Same because of CPCTC. What else do you know about those angles? In this proof, we got that, and then we said that they are a linear pair. So we can say the same thing, angle TMS and angle RMS, linear pair. Reason? Yes. Alright, so I got this beautiful linear pair. Big deal. Why'd I work so hard for that? Go back to your example. So MON and LON are supplementary, linear pair postulate. So TMS and angle RMS, supplementary, linear pair postulate. So that means what? So angle TMS, the measure of angle TMS plus the measure of angle RMS equals 180. Reason? Definition of supplementary. Now we did this funny thing. What did we do? We said that they were congruent before. So then we have a substitution. So we want to sub one of those in for the other one. So let's sub RMS in for TMS. So RMS has to equal 90. Now, I could have broke that down to a couple more steps, but I think at 12 we have enough. So if it's 90, then what do we know about the segments? RT is perpendicular to SU, definition of perpendicular. Now, the things I want you to see in this proof is we have subcommands. You notice that. One command or one piece of it was proving the triangle's congruent. Another large portion of it was then showing that the angles were the same and that they were 90 degrees and they were perpendicular. But this little guy here, definition of linear pair postulate, definition of supplementary, that's kind of a subcommand. So I know that these proofs seem, why are we doing this? You know, how am I going to use this in my life? You write a computer program. It has these subcommands in it, where it is or say you are training for, you do it if you, say you play sports, and they say, okay, I want you to run this drill. Well, that drill has these different things that make it up. When you first did the drill, it probably took you a little bit to get it. It's the same thing here. We're putting different drills together to get the whole picture. Whether it's athletics, it's computers, it's if you're working in the air control tower at the airport, you have certain procedures that you're going through before you do one thing. You certainly hope that somebody fixes your brakes on your car. They have a set of procedures that, okay, I have now installed the brakes. This is the check system that I'm going to go through. it's all about that logical thinking and what comes before what and what can we claim. Now, it's through geometry definitions and theorems, but that process